Hello and welcome everyone. My name is Niall Salter. I'm on the DS Infra team here at TV Scientific, and today I'm here to talk about the HID cache I built in Zig for our Zig bidder. I have a website, validarc.dev. If you find this stuff interesting, I have a couple of other things that might be along a similar vein that could be cool. Today's problem is that the ML team trained some models to make predictions about cluster of IPv4 addresses. In the bidder, we want to use these improved models, but we need some way of mapping an IPv4 address to a cluster. So the basic concept here is that on demand, we get a query for an IP address, and we're going to look up in some database what cluster it's supposed to be in. And a cluster is going to be some number, and all of the IP addresses that map to a particular cluster are going to have behavior that tends to correlate with each other. So we could imagine that cluster 123 refers to people who respond well to mobile gaming ads, but maybe they respond, maybe they don't like certain kinds of ads. And so in our bidder, when we feed this into our machine learning model, if we are thinking about showing a mobile gaming ad and you're in cluster 123, we're going to say, you probably might like this, so we're going to rate it higher that you might like it. So that's the basic idea. And on the infra side, we are interested in supporting this ability to retrieve clusters based on an IP address. More context, we have 170 million IP addresses we need to map. 90% of the IP addresses we need to map are IPv4s, so maybe multiply this by 0.9. I don't remember which one the 170 million was, but this is a good estimate we'll be working with here today. So the solution, the abstract data type we're looking for is a map, right? We could use an off-the-shelf map. Zig has two of them in the standard library. We could get an open source one as well. But due to the massive size of our data set, we can do better than an off-the-shelf map. Off-the-shelf maps are engineered to have generally good performance on general purpose workloads. However, our workload is not general purpose. We actually have a static lifecycle for our database stuff or our caches. And so yeah, the lifecycle is anytime there's an update to the data structure in the bidder, we're going to read an entirely new one in and delete the old one. And so we can use a static data structure rather than a dynamic one. That means that we can do better in terms of CPU performance and the amount of memory that it takes. Specifically, general purpose hash maps, they generally run at a certain load capacity. I think in Zig I've heard like 90% load capacity is typically what you expect through really good engineering on the part of the people who made the hash map. But we can do better because we have a static data set. We don't need any holes in our array. We can actually just store exactly how much data we need. The other thing about a general purpose hash map, it has to worry about non-minimal perfect hash functions, which we have one of those that we can use effectively. You'll see how that works. And a general purpose hash map has to store each key individually. We don't need to do that. So let's roll our own. We can borrow a page from a subfield of computer science known as succinct data structures. Instead of storing each IPv4 as a U32, we can save memory by storing 2 to the 32 bits, which represents the entire universe of possible IPv4 addresses. To indicate that a particular IPv4 is in the set, simply find the bit position corresponding to the IPv4 encoded as a U32 and set that bit to 1. So here's some napkin math. A conventional hash map, which has to store 170 million keys, where each one is a U32, which is 4 bytes, that's going to take 0.68 gigabytes minimum to store. On the other hand, with the universe idea, 2 to the 32 bits is 0.53 gigabytes. So there you go, right there. That's 150 megabyte storage just off the top. Just, best case for a conventional hash map compared to what we're doing. We're clearly saving information here, and we're saving even more than that. You'll see why. So let's give an example, a little demo of how this works. Let's scale the problem down. Let's imagine for a minute that an IP address can be represented as a U4. So in this universe, there are 16 possible IP addresses. So in order to store the universe, you need 16 bits. The first bit represents IP address 0. The next one represents IP address 1, and 2, and 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So this 1 bit tells us 2 is in the set of IP addresses we intend to map. 6 is there, 8 and 11 and 12. We also want to associate some data. Let's say it's this array, A, B, C, D, and E. The first bit maps to the first value, the next bit maps to the next value, the next bit maps to the next value, and so on. So you can see that successive 1 bits are mapping to successive indices. So how would we actually figure this out on demand? Let's imagine that we were querying for IP address 11, and this is supposed to map to index 3 of our array, which gets us the value, the cluster D. So how do we do that? Well, we can take 1 shifted to the left by 11, the value we're querying for, and I am showing it going right. The reason for the discrepancy here is because I wanted to show the first bit on the left-hand side, whereas numerically we typically think of the least significant bit being on the far right. So if you're confused about why it's kind of backwards, that's the reason. I apologize if that's confusing, but I think this actually makes more sense than an alternative way I could have depicted it. So the next thing we can do is we can subtract 1. And what that's going to do is 0 that the bottom 1 bit, the least significant 1 bit, and then it's going to flip to 1s all of the trailing zeros. Okay, and the reason for that is exactly what you might think. When you subtract 1 from a number with a bunch of zeros, right, what's 0 minus 1? Well, you have to carry, you have to borrow from the previous one, right? And so we're borrowing from the previous, borrowing from the previous, borrowing from the previous, until we get to that bottom 1, right? So similar to what you've seen in grade school. Next thing we do is I zero extended it for edification purposes. We're going to do an AND with the universe. And what that's going to do is it's going to preserve the bits below the bit we're querying for, and then delete everything else. And that's what the dots represent. The dots are zeros, but they're not bits of information zeros. They are deleted information zeros. Next, we're going to feed that into a pop count operation, which is an instruction that we have support for on x86. It stands for population count, and it will tell us how many 1 bits are there in the bit string. In this case, the answer is 3, which is, of course, what we're looking for. That maps to D. So at a high level, what did we just do? What did we just accomplish? We said, how many 1 bits are there prior to the bit that we're querying for? And yes, for this one, the answer is 3. For the first bit, the answer is 0. For this one, the answer is 1 and 2 and 3 and 4 for each successive bit. Okay, so let's scale back up. Let's go to U32s. That means we need a universe of size 2 to the 32 bits. Obviously, there's a scaling issue with this. We wouldn't want to have to, let's say, pop count half a gigabyte's worth of data for each real-time query. And why not? Let's do some napkin math to figure out how long this would take. So let's assume we can pop count 2 to the 6 bytes at once. So what I mean by at once, I mean in a single instruction. We can do this because AVX-512 has 64 byte vectors. Okay, there are 2 to the 29 bytes in our universe, which is the same as 2 to the 32 bits. So if you divide those, you get 2 to the 23 pop counts. If you remember the trick is that you subtract 29 from 6, right? So that's why I wrote it this way. 2 to the 23 pop counts is roughly 8 million pop counts. And you can imagine we could have like a Zen 5 machine, which could maybe do 2 of them per cycle. Okay, that's roughly 4 million pop counts. So it takes, if we imagine, yes, it's going to take 4 million cycles is what I meant to say. If we had a machine that, let's say, ran at 4 billion cycles per second, which is sort of in the range, it will take 1 millisecond to do that many pop counts. Now, that's pretty fast, but we wouldn't want to do that on demand for every single query. We want to do it as a pre-processing step. So the solution, just cache the pop count every 2048 bits. So yeah, we will demonstrate how this works. So here's some real code. Here's our query function here, and I'm showing this kind of number line looking thing. Imagine that this represents our 2 to the 32 bits, And the vertical bars represent checkpoints. Obviously, in the real world, you'd have way more than this many checkpoints, but just for illustrative purposes, let's imagine that we have some query that's somewhere in the middle, and it's right there. So the first thing we can do is we take our IP address as a U32. If you are not aware of how that transformation works, you're not used to that. If you're used to seeing it as A.B.C.D, just imagine convert A, B, C, and D to bytes and concatenate them. That's your U32. Now, the IP address as a U32 tells us which bit to look at in the 2 to the 32 bits. So in order to map that to a byte pointer, a byte array, we take the bit address and divide it by 8 to get the byte address. This universe is a byte array, so we can index into it like this. And then what bit do we take out of the byte that we get back? Well, we shift it to the right by the truncated IP. So we're going to look at the bottom 3 bits of the IP address, and that tells us which bit in the byte we're interested in. And then it's going to move it to the least significant bit position, which we can extract here by truncating it to a U1. If it's a 0, we do nothing. But let's assume it's not 0. What we do is we can align backward our IP to checkpoint interval, which in this case is 2048. So effectively what we're doing, we're just deleting the bottom 11 bits, which we can do in one instruction. And this tells us the bit position of the last checkpoint. Then we take that bit position and we divide it by 2048 in this case, our checkpoint interval. And that tells us which index in the checkpoints array to look in. So we look that up, and that tells us the number of 1 bits up to this checkpoint. Next, now that we have the checkpoint, now we just have to count the number of 1 bits in this checkpoint vector up to but not including some bit position in this vector. You can see we're reading it in here. We're doing the same thing. We say take the checkpoint bit position, divide it by 8 to get the byte position, and then we say 256 bytes from there. That's how much we're reading into the vector, which 256 bytes is the same as 2048 bits. Okay. We also want to know how many bits are we into the particular vector. So locally, how many bits in the vector do we have to pop count? The answer is the bottom 11 bits of the IP address. Okay. And then, yes, we can, what we're going to do is we're going to look up inside of the associated array here, the HIDs array is what it's called. We're going to add the checkpoint, which is this value, to the pop count of the bits inside of the vector, but only this number of bits. Okay. So it's kind of like a BZ high sort of thing and feeding into a pop count, but we're going to be doing more than just those 2 instructions. So let's go look at the implementation for x86. Okay, so we're zooming in on the particular vector here. You can see I have 32 dashes that each dash represents 8 bytes in the vector. And yes, we also have a bit position, which is a U11. Okay, so the 8-byte position that we're in is the bit position shifted to the right by 6. I could also have written divided by 64. Same thing. Okay. You'll note that this is a U5 as a result, and this makes sense because what's the range of a U5? It's 0 through 31, and we have 32 8-byte values here. Okay. So this refers to which 8-byte value are we in. Then we can pass that into a BZ high, and with a bit string of all ones. And this will give us a mask that we call U64s to keep, which is just which 8-byte pop counts do we need to know. Then we're going to do all of the 8-byte pop counts with this mask. So for the first 8-byte pop counts, let's just say the pop count of the first 8 bytes is 17, and then 33, 64, 16, 51, 24, 44, 55. Just made up numbers. And likewise for the other 3. So the reason why we have 4 vectors, just to be clear, is because it's 256 bytes. You can only fit 64 bytes in a vector. And so, yeah, at the instruction level, at the hardware level, we're going to need 4 vectors in order to hold all this data. And we have this masked pop count function, which just wraps pop count instruction. What it's going to do is it's going to take the pop count of each 64-bit, 8-byte value, like I said, and it also takes in this mask and shifts it to the right by 0, 8, 16, or 24 for these. And so the idea is we're taking some subsection of 8 bits. So for this one, it's going to be these 8 bits. And wherever there's a 0, we're just going to zero out the pop count. We don't care what it is, because we're just trying to add up what's the pop count of values that come before the place we're querying. So to get the pop count up to the last 8 bytes, what we can do, we can add A and B and also add C and D in parallel. That might look like this. Now, I should say that this masked pop count function, this actually returns our result as an array of 8 bytes. And the reason for that is because of specifically how we want to get all these additions done. But yeah, you might notice that we're not adding the result of A and B to the result of C and D, which we could have done directly, right? But because these are bytes, when we add 64 and 64, that's the maximum possible value that could result from counting the number of 1 bits in a 64-bit integer, we get 128, right? Now, if we also had 128 over here as a result, then if we try to add 128 and 128 inside of a byte, we're going to get an overflow. And so we need some other trick to add these up. The trick that I chose to go with is this haddlane function. What this haddlane function does is a horizontal add of the bytes. We have an instruction which does this. It's actually packed sum of absolute differences. And yes, what we can use this for is we can add all the bytes in a vector of 8 bytes together in one instruction. Takes 3 cycles. And what's cool about it is it actually gives us the result as a U16. So we don't have to worry about overflow here. We can add the 2 horizontally added values together, and then we can, then we're done. Now we're zooming in on the individual 8 bytes, and now we're going to find the pop count within the individual 8 bytes. So let's say our query is this orange 1 bit over here. Let's say that's the IP address we're querying for. We do the same thing as before. We do a BZ high with the bit position, which is just the bottom 6 bits of bit position here, which we got from the top. That's just our IP address. And yes, we take all the bits up to but not including the bit we're querying for, and we feed that into a pop count instruction. In this case, we happen to get 13, and we can add those together. So what did we just do? We are going to add the value at the checkpoint, which tells us the number of 1 bits up to that checkpoint. Then, for a particular 256-byte chunk, we add up how many, for however many 8 bytes in the 256-byte chunk there are that come before the bit we're querying for, we want to add up the pop count of those. Then we go to the 8 bytes that we're in, and we find the pop count of the bits up to but not including the bit we're querying for within that. We add those 3 together, and that tells us for the whole data structure what's the number of 1 bits prior to the bit we're querying for. And we can, of course, look that up in our associated array, and we're done. So, in conclusion, we made an HHID cache with guaranteed space and memory constraints. Amazing. Here is the godbolt for that, for the pop count bits function. You can see we load in 4 vectors of 64 bytes into ZMM 0, 1, 2, and 3, and we're going to pop count them. This Q is short for quad word, and it refers to the fact that we want to pop count the U64s within this 64-byte vector. And so yes, what we do with this is we feed these into VP move QB instructions. And effectively, we're turning the U64 answers of pop counts into bytes because we want a vector of 8 bytes. And you can see we have this mask K1, which came from ECX. ECX came from this BZ high instruction that we were talking about before. So this is figuring out, right, how which 8-byte section are we in. And then we're distributing this mask K1 to each of the VP move QBs. And you can see we're shifting to the right by 8, 16, 24, just like we said. And then we're doing 2 sets of adds here with byte granularity, just like I showed. And then we're going to do the horizontal addition of each of those. We're going to add those together. And then in the end, we're moving that to a general purpose register, RCX, which we're adding to RAX. RAX is the pop count of the previous RAX, which we got from the BZ high of the particular 8-byte value that we're in. So yes, this solves our problem, and we can run it in 25 cycles on a Zen 5 machine right here. We also, this isn't a perfect simulator, and this doesn't include the memory access time. Maybe it's in cache, maybe it's not in cache, but the instructions themselves are relatively fast, as you can see. So that's all I have for today. I hope everyone enjoyed, and I will see you next time. Goodbye.